Okay, we're starting the afternoon session, and Alessio, you can start presenting.
So, hello everybody. So my name is Alessio Menavoli. I am associate professor at Trinity College Dublin in Ireland, and my title is what do we want to do? So recently, I try to say stop to try to work on paper and go back a bit to do a bit of reading, because I wanted to try to understand what do we want to do, and try to see, what kind of results have been already derived, what is the relationship between these results, what I think it's useful, for what we want to do. So this talk is more about, try to present some of the results. Gert already presented something about imprecise probability, so this is easier for me. And then I will try to show some of work that I've done with Marco Zaffalone and Alessandro Facchini on quantum mechanics and on the generalized probability. Okay, so what do we want to do? So is this what we want to do? We have seen this figure before. So we want to represent, preparation procedures in physics, where we want to prepare some object, and we want to do measurement. So in a more, let's say, a general way, preparation is a list of instructions we do to perform an experiment, to prepare an experiment. And then we have some measurement detector that we use, that are instruction that we perform after preparing the state to get some reading, some real number. And then we can also have channels, so we can, do some, what we call, evolution or transformation after preparation or before measurement. Okay, so this is the picture. And what we saw at the end, we use mixture spaces for this, and we can call these many ways, test function, random variables. Okay, so for this side. Okay, well, this is the picture. Okay, so I want to go back to a different field. So yeah, this gave the overview of somehow precise probability with Definetti and Pascal and so on. And so I went straight to economics, because also there we want to do the same stuff. Okay, so what we want to do in economics is to model consumer. Okay, so what is a consumer is someone that has preference. Okay, so we have preference, can be over cupcakes. So what does it mean that you prefer these to these? It means that if you can think of a cupcake as the recipe of this cupcake and the recipe for this, means that you are preferring the recipe of X more than the recipe of Y if you prefer this cupcake to this. Okay, so what do we want to do? What do we want to do in economics is to start from preference and derive a representation. Okay, that usually is through a utility function. And the idea is, okay, if this preference satisfies some axioms, at the end it means that in your head you have a utility function. Okay, and that means that if this is better than this, means the utility of the recipe of this is greater than the utility of the recipe of this. Right? So this is the utility representation theorem. But then, okay, there is an issue. So when you go to a bakery, you buy a cupcake, you don't receive the same cupcake every time, but there is some uncertainty. Okay, so there is uncertainty where the uncertainty, what we call it in the preparation procedure. Okay, so sometimes you want to buy this cupcake, but instead maybe you get different recipe. Okay, so for instance, let's assume that the recipe is amount of butter and amount of sugar. So this is cupcake 1, 5 grams of sugar and 3 grams of butter. The scale is here. Is another cupcake. And so it means that when you buy it, you have uncertainty. So let's say with probability 1/3, you get this cupcake, or with probability 2/3, you get this other one. So you have a probability over the cupcake, or you can have another one. Okay, 3 divided by 4 this, and 1 divided by 4 this. Okay, so this is you have this distribution that represents the uncertainty of the preparation of the cupcake. And so what do you want to do with this? And the famous for Newman-Morgenstern theorem tells us basically that try to generalize the utility theorem we saw before to the case where you have uncertainty. And the idea that you have these probabilities, they belong on some space, so you can mix them. and to get this mixture, where alpha is a mixture, a weight between 0 and 1. And so at the end, also this is a valid recipe, and they all belong to a mixture space, okay? And the space of probabilities. And then at the end, what you have, so instead of having preference over cupcakes, since at the end you don't buy cupcakes, but you buy this uncertainty over them, you have preference over the distribution. Okay, so the idea would be, do you prefer this distribution to this? Okay, so this is the idea. So in this way, you model both what you like, but also the uncertainty. Okay, so, and then for Newman and Morgenstern, derive this famous theorem, that is the famous expect utility theorem. And the idea is that if you have a preference over this element, this probability distribution, P and Q, and so on some set of recipes, okay, there's an assumption here that these are finite support, just make things a bit simple. And if these preferences satisfy certain assumptions, that is completeness, so basically this is sort of total order, so you can always say that you prefer this to this, or they may be the same. Independence, it's another axiom that you will see in a second why it's needed. And continuity, it's what they had before called the Archimedean axiom. Right? So again, it's a sort of topological assumption. So if you have this relation, so if you have preference over this distribution and they satisfy this axiom, it means that in your head, okay, you have a utility function again from this recipes of the cupcake to R, and that means that you prefer this to this if the expected value with respect to P of this utility is greater or equal than the expected value of the utility with respect to Q. Okay, so basically, your utility represents the preference, and this P and Q here model the uncertainty on the preparation.
But U is not a linear function, right? It can be anything.
This at the moment is not. It's you can impose, you can add constraints, but it's not. Okay? And so in this type in economics, they care about two things. One is the representation theorem, and then the uniqueness. Okay, is this U unique? The answer is not. So it's unique up to an affine transformation. Okay? So this independence axiom here is necessary to have this product here. Okay, so U times P. And the completeness is what that makes the fact that you have, apart from this class of equivalence, you have only one utility. Okay, if you drop this, so for instance, you say, given to cupcake, I don't want to decide because this tests better and the other looks better. So in this case, you don't have a unique U. You may have multiple U's. Okay? So in this case, this is the completeness. So apart from this equivalence class, you have only one U. Okay, so when I look at this theorem, again, it's for Newman, Morgenstern was an economist, okay, but what we all expect, that for Newman realized that this is basically, again, foundation of quantum mechanics. So what I was being surprised that if you go for Newman book, about mathematical foundation of quantum mechanics, there is no reference to this theorem, although book was published. So why is this what we actually are trying to do? Because there was someone, again, economists in 1953, that decided, okay, let's take the theorem we saw before and let's try to generalize it. Why should we care about P and Q being probability distribution? Can we generalize to any set? And then they said, yes, so we define a mixture space. Okay, so what is a mixture space? Is a space with some operations that generalize the mixture of probability distribution. Okay, so we have a set, we define, as we have seen before, Gabriele calls this P, we call it alpha, it's the same, okay? So we define an alpha mixture of X and Y. I denote this in this way, okay, not in other ways, but basically this notation, so we have two objects, X and Y, every dual mixture, is the generalization of this expression. Okay? So, and then they define some properties. Okay, so this is, you can think, you can try to understand why this process by comparing, this with this case. Just have an intuition, but this is associativity, this is the fact that if you mix X with X, you get X. And this is the famous property that you've seen before that was there. Okay. The problem that if you mix X and Z and Y and Z with the alpha, then X will be equal to 1. Okay. Okay, so they did this because they want to generalize this. Okay. To do that, basically, the proof is as follows. So you have this, and then, so this is the theorem that they proved. That is, okay, let M be a mixed space. Okay. Then with those properties that you have seen, then there exists a vector space V over the real numbers. Okay. Why real numbers? It comes from this. Okay, because they define the operation, the proof that exploit the fact that this is a real number. And the real number is a function phi mapping the mixed space into the vector space that satisfies these properties. Okay, so F is 1-to-1 into the cone K generating V. So why a cone? I'm going to see this in a second. So why a cone? Because remember, so what they wanted to do is to then impose an order, and that's why you need cones. Okay? Yeah. So that's why they needed to do this mapping with the cone first, and then through the cone they define the vector space. So this function phi satisfies this. I've already seen this. They are fine combination or call it the linearity, depending on how you want to see it. So basically, the mixing comes out of phi. And then, so this is the most important, the mapping of the mixture space into the vector space is a convex set. So if you do the convex Al, you get this. Okay? So you map mixture space into a convex subspace of the vector space. From this, you can build a vector space, okay, through the span, this element, and you can also write a fine combination of these. And important, this does not include the 0 because basically they want to prove basically that is one-to-one mapping and all the properties of the code. So you need this in the proof. So you have this result, okay? And this is basically, once you have this, you have generalized the structure of this theorem to things that are not probabilities, but general things. And then what they do, they impose an order of these new things, and then derive a representation like that. And I'm not going to do that, but just I'm going to show how the proof works, because it's what actually is interesting for us. So the proof is, I think we have seen this today in the slides from Gert, works the following. So we take a mixed space. Let's take an example just to understand like probability of X. So we have a coin. So there are two ways we can define a mixed space here. Okay, so the first way is just take the probability of X. We forget tail, so this is a mixed space. Or otherwise, we can consider P and 1 minus P. Right? These two are equivalent. So if you do this, the basic idea that you embed this mixed space in R2, here in this example, where basically you have the probability of Z is the X coordinate, and Y is always equal to 1. Right? Within this one is the normalization of probability. Okay? So the unit here is 0, 1. Okay? So this is the unit, right? Because it's this that you care about. Or the other way, you can embed it in this way, where each element of this line is P 1 minus P. Right? So 0, 1 or 1, 0, alpha is here. Right? Two ways. The proof doesn't start with this, but starts with the cone. Okay, so first they define a cone. In this case, it's this cone. In this case, it's this. And then they define the mixed space by looking at a cone cross section. In this case, this one where the fixed one here, or this one where all the elements sum to 1. And to do that, they need to basically go from here, from this from the element of the vector space to the element of the mixed space, so this operation to the cone by defining basically a an addition and a scalar multiplication that is compatible with the operation of the mixed space. So this is the way we define this cone. Okay, then when you have this cone, then you can build the vector space by doing the span of this difference. Right? So there's this vector space. So now the result is proved because then you have that your mixed space is embedded in the vector space. Okay, so now you can work in the vector space and it's done. Okay, so what we can do next is, okay, we can take the dual, so we have a vector space over the real numbers, and we can take this mathematical dual that is defined by the linear functional on the vector space to R, and when we have the dual vector space of this linear functional, we can compute the dual, the cone, blue cone, than before by taking the bilinear form here and checking for taking all the G in the dual, such that we call it the inner product. As an example, is an inner product in general is this bilinear form. This is greater than or equal to 0 for each element k in the blue cone that we have seen. So here, I didn't talk about being close. This is something that probably we don't need here, okay? But you want to remember that get in the cones, we didn't just care about the border. No, here we can take this to be close. So, as we have seen, we can be a bit, we can be more general, okay? But let's assume we take that close. Okay, so we have this. And then what we have defined this dual cone, dual vector space, and then we can define, as we have seen, this unit. Okay, so we define this dual vector space, this unit, and it's the same unit gamble that get defined in a way that. So why do we need this unit? Because this allows through this duality to characterize the element of the mixed space. So the element of the mixed space as those, they are normalized. Okay? So this is important because basically, as we have seen when we define probability, prevision, we need this constant. Right? So this unit is very important because characterize the element of the mixed space. So once we have a cone, we can define also an order. We can say that G is preferred to H if the difference is in the cone. And another thing that we want to add as a property, we want to have that this vector space and this order unit satisfy this property. Right? That is, if the vector space, a vector space with this order is an ordered vector space, if the unit satisfies this, so for each G, there is a lambda such that lambda times the constant is preferred to G, okay, for some lambda, then the vector space is as an order unit. So why this is nice? Because basically this way we can avoid to define the norm, and we can define a norm through this order. Right? So it's another way. So get before define the supreme norm, could equivalent impose this. Okay, so these are the properties. So let's do an example. Two examples. So in this case, the dual cone is this. Right? So how do we define it? Remember, through this inner product. So what is this? Is the element. Okay, so then multiplied by this is 0. Right? So this is the way we define it. So this is orthogonal to this, and this is orthogonal to this. So this is the dual cone. In this case, that is probably the nicer case, the cone is self-dual. Okay, so dual of this blue cone is this cone. Okay? So what we have done here now, we have started with this abstract mixed space that was, in this case, was not too abstract because we started with the probability, but the idea will be that we define the cone, then we define this dual cone. Right? So these objects are always related. And so this is in such the map. So here we are taking all the mixed space, the cone, and taking the dual. Okay, but sometimes this is where we have that order. So remember what usually for Newman want to do, we'll just go back, is to impose some knowledge or preference, okay, over these probabilities, just to say that not all the elements of the mixed space are the same. Okay, so there is some preference of a consumer, and that's what happens in this picture with this preference. Usually what happens is that instead of considering this is the general mapping. No, it's the idea that you restrict by giving this preference, you restrict the cone or the mixed space. So maybe from your preference, understand the probability is instead of you thinking the coin be anything, you may think the coin be close to be fair. So the probability is between, I don't know what is like 0.4 and 0.5. Okay? And then we can take the dual of this. Okay, so usually what happens in this picture, so if you restrict it so if you have more information, this cone here becomes smaller, and this one in the dual becomes bigger. Okay? But what we care is this mapping. Okay, so this is the mapping that is connected to the representation, and this is the knowledge you want to add more. Okay, so in general, so let's just summarize here. Now we have a preparation. We saw that preparation we want to model mixed space, and we saw that from that theorem, we can always embed mixed space in convex vector space under those assumptions, of course, for the mixed space. And by duality, we can have this dual cone. We can call them utilities, or effect measures. Okay, so this is the duality that we have. So the preparation is the mixed space through duality. We get these other objects. Okay, so the object that we compute expectation of. Okay, so this is what the object. Okay, so and then in a moment I'd like try to stop here and try to understand why this duality is a bit better, in particular, sorry, these two. So yeah, the nice thing about these cones, these cones are self-dual. Okay, so you take the cone here, you get the same cone. This one, they are not, but these representations are isomorphic, so you can always map this one to this one. Okay? So we can always assume that in this case, the cone are self-dual. So why do we care this cone to be self-dual? Because basically there is a particular class of cones that are called the symmetric cones that have these properties, so are self-dual with respect to the inner product we are considering, and they are homogeneous. Okay, so what it means here that there are linear transformation in the space that map each that you can map any element of the cone from one to another through this linear transformation. Okay, so this is what means homogeneous. And why do we like these cones that are symmetric? Because on those cones you can define two things. Okay, so first you can define like a spectral decomposition through Jordan algebra. So we didn't discuss, we discussed about Lie algebra and the Jordan algebra. I think somehow it's related. Okay, and moreover, you can through this spectral decomposition you can define determinant and logarithm. Why do we care about this? Because then you can define an entropy. Okay, so consequence. So let's talk about this. What is this transformation? Okay, so these are the transformation that preserve the positive cone. Okay, so for instance, what are these transformations? Okay, so again, we saw this again. So if you focus on this cone here, okay, that is a coin, probability, classical probability. These transformations that preserve the cone are permutations. Permutation, if you work with the quantum mechanics, these transformations are unitary operators if we focus on the density metrics. Okay, so this is the property of this. So when you end up with this, you have these properties. And a nice thing about this, so this is my view of generalized probability theory. So what we want to do, that at the end, what we try to do often I feel that is to end up here. Okay, we end up here from different direction, and then we try to use one property maybe to characterize the other. Right? And so for instance, I think what Gert did, it was nice. So we try to characterize the positive cone maybe from this transformation. Okay? Or vice versa. Or use the entropy. Okay, talk about this. Okay, so the nice thing about this is there is a theorem that tells us that every symmetric cone, right, is unique up to so it's a unique direct sum of irreducible cones. Okay, so what does it mean? That if you think about symmetric cones, all the symmetrical you can think, there are not many. There are only these 5 types. Okay, you can always reduce to this cone here. It's not symmetric, but you can map to symmetric cone. Okay, and there are only 5 symmetric cones in finite dimension. Okay, because here the dimension is fixed, and these cones are the Lorentz cone. Okay, so relativity. Okay, the cone of real symmetric positive definitive matrices, the cone of Hermitian positive semi-definite matrices is this cone of quaternions, this is the octanions. Let's forget about these 2, but these 3, at least what we use a lot. Okay, so in particular, we know this, and classical probability, you can take this as a particle case of one of them. So this is these amazing results. So why do we care about this? Again, because all these cones have this property are the only ones that have these properties. And then if you look at a lot of the derivation of generalized probability theory, so what the idea is to define some properties that are not mathematical properties like this, but more like property coming from physics. But all these properties try to single out some of these characteristics. Okay, for instance, this you can think of being a duality between measurement and states. Okay, so this is what it means. So you want to see a measurement as a state too. Okay? And this is clear. The homogeneous transformations, the evolution. You want to preserve the properties of the symmetry. And so the symmetry actually is this plus this self-duality. Okay, so why do we say that? So just a bit of mapping of what we are talking about. Okay, so let's go to finite dimensional quantum mechanics. So the embedded mixed space. So we have a mixed space there. At the end, we are embedding it into this convex subspace of the space of Hermitian n by n matrices. The cone, the blue cone and a red cone that you have seen before, they are self-dual, and these cones are the cones of the positive Hermitian matrices. Okay? So these are the blue cone and red cone in quantum mechanics. The inner product is the trace. The homogeneous transformation of the positive cone is this. Well, it doesn't need to be unitary, actually. But, okay. This transformation, if I just focus on the mixture space, so on the density matrix, since I want to preserve the unit, I need this to be unitary. And I can take, for each cone, then I can take the log of any element, okay? Because it's well defined through the spectral decomposition. And once I have this, I can define the entropy, entry, for instance, through this tensor product. And you can do the same for all those cones. Okay, so there are all these properties. But there is a very interesting thing about these cones that in Jordan algebra, there is no unique way or an elegant way or we call it a natural way to define a tensor product. Right? So there is no, it's not in the direction of the algebra. And so when you define it, the tensor product on this structure, on these cones, okay, since this is not like, say, they don't behave the same in each of these objects, you can use basically the property of the tensor product in one of the cones, for instance, to distinguish quantum mechanics from the other. Okay, so quantum mechanics, in particular, this object here is the one that behave nicely through the tensor product. Okay, and the reason is because of the imaginary unit. Okay, I have an example later to show you that. But as in basically, it's a lot of in generalized probability theory. You end up here, and then you want to pick up this. How do you do that? By defining this, by defining some property of this, because it's the only one that satisfies this. Okay, so this is a bit of summary. And so what I was trying to start to work with this in this framework, but then I was not satisfied about this because for two reasons. Because so each one of these structures, so you see here, is defined in an independent way. So you are in quantum mechanics, you work with this mixed space. You are here, you work with this object. You are here, you work with this object. You are with the coin, you work that with probability. And the idea will be, but can we in somehow abstract to go a bit in a higher space or in another, let's say, another representation that allows us to talk about all these objects at the same time. Okay, so I want to have something that is general enough, okay, to be able to, for instance, compare quantum with classical probability. And why? And also, while I'm doing that, there were some statements that when for instance, when you read paper about the generalized probability theory, you see that, for instance, some of these statements that I didn't think to be true. Okay, in the sense they are true, but they are not. This is not true for all classical probability theory, as we see in a second. For instance, one thing that a lot of people they see, if you take finite dimensional quantum mechanics, they see classical probability theory as a particular case of quantum theory if you restrict to density metrics that are diagonal. Okay, so this is one statement. So CPT is included in quantum theory. Okay? The other is classical probability theory. Okay, in finite dimensions, the only theory in the framework with unique decomposition of all mixed states.
By the way, the first is not going to work for on the continuum.
So this is one of them. This is why I didn't like. Okay, and okay, it's a very particular case. So you are plotting the structure.
Exactly.
That's why I don't like it. And this one too. Okay, as I see, it depends on what you see. How you see classical probability. What you are comparing this with. And then again, this is what Gabriele was saying this morning about how we saw it with the block sphere before, is to have multiple basis functions. You can decompose the state in multiple ways, and this is something that you cannot do here. Again, it's true if you look at the diagram. And the third thing that is what you are mentioning, that this construction here, they don't work in the continuum. So if you try to extend it to the finite dimensional continuum, to say finite dimensional quantum mechanics, they don't work. Okay, so there is no way to do it. So you're stuck with this structure. Okay, so we try to do a step back and to try to derive these things by being more general. Okay, and what we did is to try to look at this. And what is this? Okay, so this you can think about when you do an experiment, what actually you are defining with your preparation devices and the reading, you are defining a function. Okay? A function from that is a function of the preparation, the measurement, and at the end you have the reading, a real number. Okay, so you can represent it in different way, but you can also think this as being like say the subscript of the function. I use the measure to characterize the function itself, and I see as a function of the variable that is the preparation. Okay? So I can always do that, just decide what is what. Okay, I can basically the idea I can put this fixed and I change this. Okay, so we took this function and say, okay, so what do we do now at the end in physics is to make this function, this experiment, and then we measure it. Okay, so then we have a reading. And so what we do now when we want to write down a theory is to try to understand what is happening here. When we have evaluated, we have made an experiment, we have made a function, and then we use an experiment. So this is important to evaluate it. Okay, the experiment evaluates the function. The experiment returns this number. Right? This is what is our approach. Okay, so we build a function, and then the nature of the experiment evaluates it. It returns me another number. And what we do in physics is to try to understand how this and these two are related, given this, and try to come up to a model, with a model. Okay, so what do you want to do? Okay, so so I want to go back. And to do that, what we assumed at first is also that when we build an experiment, we want to have a class of functions, okay, that we can represent in a vector space. So why? Because I want basically to be able to say, okay, I have this experiment, I have another one, I want to combine the results, okay? So I want to be able to sum experiment, this to be also an experiment, or to put a scaling here, to have an space. So for me, it's convenient to have a vector space here, in a way that in this way, I can basically, in somehow, represent this experiment in a close way. So if I combine them, a sum, or multiply by constant, still this function remain in the same class, in the same vector space. Okay? So I want basically have a class of function, okay? Because in this way I can characterize all the experiments in the same way. Okay? So this assumption, this belongs to a vector space. Yeah. Okay, so and now here it's go back to get, get introduce the problem. So we look, okay, but if you have this function, you look at the experiment through this function, how do you represent your belief? So in the preparation of mixed space, you are mixing preparation. How do you represent what you expect about the result of the experiment here? Okay, so there is a way to do it. That is, there is seeing these G functions again. Okay, so somehow you prepare an experiment, you prepare a G, and then you try to use this G to bet on the result of this experiment. Okay, so we saw this morning we get, I'm not going to go to the accept reject framework. I'm going to use it's a simpler framework, where you are only say desirability, without distinguishing between acceptance or rejection. And I have here a little example, maybe to make this a bit clearer with this function, and is just to give an idea. The example that I use. What does it mean to make a bet here? So imagine that this function, if you want to make, how tall was Einstein? Okay, so this is what you need to bet on. Okay, and let's imagine this is an experiment. Okay, yeah, so we know the truth, but okay. So do you want to bet it? So let's say that we need to fix the possibility space. So we have that variable x. Okay, we need to fix possible value, see between 1.5 to 2 meters, 6 feet. Then we have a function. We assume here that the function is bounded. Why? Because of the practical reason when we do an experiment, somehow we want the function, the reading, to be always finite. This is what our assumption. We don't want to have an infinite in a reading. Okay, so we assume the function is bounded. And then what is this function? It's a function of x, right? It's my function g of x. Okay, and so what is the idea of representing this function as a bet? That is the function. If Einstein height was 1.8 meter, you get $0.75 if you accept this function. So for each value, you can see the positive dollars that you gain. In this case, here it's negative. So if Einstein height is 163 and you have accepted this gamble, you will lose money. Okay, 0.75 this way. So these are the functions. And so we want to represent an experiment with a function like that of the variable we care about, and represent our belief about the result of the experiment. In this case is Einstein height, by say if we accept or not this gamble. Okay, so if you accept this, what is the idea? That you probably believe that Einstein height was this side, and this. Okay, so what are the properties of this function as Gert showed before? So there are some gambles that I don't need to ask if you accept or not, because I know you will. Okay, if you are a rational. So the positive gamble. Yes, if you give any function that is always positive, these ones, you are going always to accept them, because no matter the height, you win money. Okay, so I know that if you are rational, you're going to accept all the functions here. So these are the tautologies, or as they call it, the background. Okay, it's what I know in this problem. And so I know that you will always accept this positive function. The positive function in this vector space with this L greater than E. Okay? Which is going to be the case. Now let's assume you accept this red and the green function, and all the positive one, all this part. So we saw before that I just keep this because we have to explain this, that what we do now, we assume this conic combination. So if you accept these two, you accept also, and the positive, because the positive always accepted, you have also to accept all the positive combination. Okay? This is the second axiom, is the linearity axiom. It's called because it's the axiom that gives you the probability theory later. Okay, and then there is the last one, that again, it's a sort of tautology in the sense that if you accept this, so let's assume you accept these two functions and the green. So you can see from accepting these two that there is something wrong, okay, in your desirability, because these two, you can see they behave opposite. So if you accept this, in somehow you're believing Einsteinitis is here, this side, this, and this side. Okay, so this is something wrong to accept these two. And in fact, if you sum them, you have this negative function. Okay, so if you do the positive of these two and the positive, you're going also to have this function that is negative. So if you accept these two, you're also accepting this negative gamble that is inside here. So you are basically a sure loser. You're losing money. So this is not rational. Okay, so these are the axioms. Okay, so tautology is positive, that is called also deductive closures, closing, what you accept. And there is this coherence axiom that simply tells you don't accept negative gamble because it's wrong. Okay, it's irrational. And in probability it's called the no-Dutch book. In economy it's called the no-arbitrage axiom. And okay, so if this is all your set of gamble, we have seen it's convex cone. Again, if you can close it or not, close it. And okay, so this is again the things that is interesting. So now that we have this cone, we can again, that is in a vector space, we can again take its dual. Okay, take the dual. So we have a cone. Let's assume that satisfies its properties, is inside a vector space of this function g, and so we can take its dual. So what is the dual? Is the dual is the dual of a linear function and the dual of a cone. In this example of the Einstein example, what is the set of linear function belonging to S, we'll characterize this S in a second, such that the linear function applied to every gamble G in the cone is non-negative. Okay, so this is the dual of the cone. So what is S? So actually you can prove that in the example of Einstein, where we take the positivity to be, go back here, be this positive function here, this S, I call it the set of states or belief states, are the set of linear functionals that are normalized, so L of 1 is equal to 1, and L of H is greater than or equal to 0 for each H in the positive cone. Okay, so this is what is. These are, you can think of this being expectation. Right? So these are the set of expectation operator that are 1 when computed on the constant gamble 1, and they are positive for each element of the positive cone. And again, so this is the dual. So we start with this cone, we get this dual, this is the set of this linear function, and we can stop here. Okay, we have our dual. So this basically will represent our expected value in classical probability, or trace rho times matrix in quantum mechanics, as we will see in a second. But we can also do another extension. So we can extend this operator to the space of measures. Okay, in particular, what we call are charges. Okay, so these are the charges are finite additive measures. Okay, so are probability that they are not sigma additive. Okay, so why? Because when we work in, especially in finite dimensional case, this is enough. And so what is, so instead of writing the dual in this way, through this extension, okay, we can also write the dual as this dual, this L, okay, as an integral, so this LG, can write as an integral of g of omega, integral with respect to this probability charge greater than 0. So this is exactly this, LG. Okay, so the dual cone, I can also write in this integral. In this case, instead of having a linear operator, I have these charges. And what is the equivalent of S is the set of charges that are non-negative, okay, and they integrate to 1. So this comes from this, and this comes from this. Okay? So it means basically that once I have this function, I can also represent as an integral with respect to these charges that are basically, the probability charges, this one, that are simply, finitely additive probability. Okay, so let's again see visually for the coin, sorry. So before we started with this to get this as dual, now we started with this side, with these gambles. Okay, these are the gambles. This is the positive cone of the gamble that you always accept. And through duality, we get this operator L, okay, and L of 1, so L of the constant 1, here is equal to 1. Okay? So this is the dual of a linear function, and this is the space of K. Right? So if I restrict my probability to this, if I have some belief in terms of desirable gambles, this is the code. Okay, so now I just try to, so we start with this, nothing different. So the only difference that here, as you see, we try to work with function, okay, that may be on some variable that this can be like continuous variable, element of R or element of complex number. And okay, so now we try to understand, okay, how can we characterize quantum mechanics or from look at the property of this function and the positive cone, and we somehow try to end up with some property that is very similar to what you're saying, being like, for instance, second countable. So we want something that allow us to make, to deal with the infinity case and be able to decide. Okay. So in a tier of desirable gambles, what you do, so you have these properties, a 0, 2, not accept positive, reject negative, and the conical, and you want to be sure that you can satisfy this property. Okay, what does it mean in practice? Okay, so you have this function that is the experiment. So you build the experiment, nature evaluates it, okay, but you need to satisfy, to be sure when you accept this gamble that you can assess or verify this property. Okay, to do that, okay, what you need to do is at the end is to solve this problem. Okay, so to verify, for instance, that your set of gamble does not include any negative gamble, you need to verify this, that for the gamble that you accept, the blue and green that we've seen before, okay, there is no positive lambda such that this function is positive. So if this is the case, it means you are also indirectly accepting a negative gamble. Okay, so there is something wrong with your theory. So if you accept a negative gamble, you cannot recover a dual, you cannot recover probability. Okay, and then we say, okay, now let's assume that we have this vector space here of function. Okay, can we solve this? Can we verify function that this property holds? Now, if you take a generic function of variables, okay, this problem is undecidable, right? If this is infinite, so if this variable take value on an infinite space, you cannot decide this. Okay, so what does it mean in practice? Let's try to understand. So you are doing an experiment. Okay, so you have your function, you build it through the experiment, and you want to verify, for instance, that this function is not a negative, right? Because you don't want to accept a negative gamble. Okay, how do you do that? You need to be able now to check that this function is non-negative. Right? And if this is a generic function, you are building a generic function here in this vector space of function, you cannot decide that. Okay, you cannot decide it. And so, okay, so maybe we said, okay, so maybe when we look at this vector space, we should restrict this function. So we used to restrict the function when we use to prepare experiment to function for which we can assess if a function, for instance, is negative or non-negative. Okay? And so what we did, we say, okay, let's take a vector space where we can decide this, and one of them, okay, is the space of polynomials. If the space of polynomials, we can decide this, yet, no, for polynomial, to assess if a function is positive or negative, polynomial for n variables, it's NP-hard, okay? So instead this is decided, but it's hard, right? And so what we concluded on the classical probability theory, in this, when these variables are continuous, so I want to use this theory of desirable gamble to derive classical probability theory in the infinite case, then basically, if I choose generic gamble, this probably is undecidable. If I restrict to polynomials, that is a nice vector space, this NP-hard. Okay, and then what we did was, okay, so let's try now to approach this problem and see what happens if we change our theory of desirable gamble in a way that allows us to compute this in an easy way. So what we did is go back to the axiom and try to do some research. First, we assume that all these functions are polynomials. Okay? Why? Because in this way, we can decide if a function is positive or negative. Okay, so this was the axiom before. Accept all non-negative polynomials because they give you a reward. Okay?
Where the gambles bounded?
The gamble are bounded, so good question. So we fix polynomial, but we bound the space. Okay, we assume that the space is bounded, and we keep the polynomials. Okay, that is general enough because, as I said, the idea would be to model an experiment. What you're reading, it's a number, so you don't want it. Yeah.
The possibility space is compact.
So it's easy if it is okay.
Yeah.
But yeah, so maybe you could think about maybe a bit more generic, but in this case, yes.
No, but I'm just wondering because then if you take the closure of this set, then you get all the continuous functions for free, right? In a way.
Exactly. So this is why you take the polynomials because of Weierstrass theorem is general enough. Yeah.
And when you talk about the complexity of like deciding whether this is there's some kind of algorithm, what is the input? Can I ask like for I don't know, finitely many values, or as often as I want, ask for any value of the function at some point? Or what does it mean to say it is NP-hard to decide whether this function is non-negative? Like how?
Okay, so think about just to make an example. Think about a polynomial, multivariate polynomial.
Yeah.
Any variables. Okay, and you need basically to decide if that function of the variable is positive or not.
Yeah.
Okay. So to do that, there is a procedure. To do that, okay, there is an algorithm. Okay, to verify that. Okay, but this verification. It's NP-hard basically means that in the worst case, you can have an exponential number of steps to do it.
So what do how do I get this function? Like, do you tell me the value at any point? Like, I understand if I had an arbitrary function, I would need to ask for infinitely many points to check for every single one.
This is remember the goal here. Okay, so you are setting a function of your experiment. Okay?
Yeah.
So these are your functions. You have done your experiment. Okay,
Yeah.
And you are here. Okay, so now you need to be able to apply this theory, you need to verify if this function is positive or negative. Why? Because if it's positive, you want to accept it. Okay, how do you do that? So imagine you don't have this function. You don't know that this is the expression of the polynomial. Okay, so you need to find a procedure that by evaluating this variable tells you. Okay, so
yes, but by taking data.
Exactly. So you don't have the function.
Yes.
You don't build the function in the sense that you need to evaluate the function to be sure that it's.
So your function is an oracle. In a way.
Yeah, you don't see it. Okay, you don't see it.
You know that you can calculate it.
Exactly.
You're not calculating, you're experimenting.
Exactly. This is the second important part. It's not you that is calculating, but it's the experiment.
Yeah.
The experiment is evaluating the function. Okay.
So based on data, I need to be able, there needs to be some procedure to decide whether this
Exactly.
is reasonable. Okay.
Exactly.
In fact, so if those questions, if those numbers are continuous, I'm never gonna be able to evaluate it because I'm never gonna have complete certainty on my inputs anyway.
Wait a second. So, okay, so this is another question that I think it's a good point, and also then I also will question this. Okay, because so this is something that you actually we thought about, that should we focus on rational number, for instance, or things like that.
No, that's not the problem. You should just use topologies. Like the only thing that you know is whether points are in an open set. That's what you know experimentally.
Yeah.
And then if you do that, it automatically works for continuous or discrete because
No, of course, no, yeah, you need to assume some topology. Actually, no, we needed to do it also to derive the dual. No, and
so the real thing that you would be doing is that you have the result of experiment. So you have an open set on R, and then like you know that the inputs were inside open sets of each of them. So you can take the inverse of that, and you know that the inverse of that is a superset of the products of those open sets. That's what you have information on it. So that's what
yeah. But remember that, so I agree with you, but remember that for the moment, what I want to, I'm not going, so the goal is to see from an experiment point of view.
No, but if you're trying to do things motivated by experiment and you're trying to model the experiment, you have to do it in a way that that is representative of what you're trying to model. If you're trying to model the experiment with infinite precision value, it's kind of you're ready.
I totally agree with you that in practice here you cannot, for instance, the preparation you cannot set infinite precise or things like that. I totally agree with you. This is an abstract way. So this is something that you need basically to make it to discretize this. These are just the limit of it, and also the other thing that it's something that we think about. If you really need, so for instance, when you take your coefficients, we are thinking about also the coefficients. If this polynomial can be real or not. Okay, so this, for example, this is a result about NP-hardness here. Okay, and as we will see in a second, the way we resolve it, and somehow there is an issue with the precision. Okay, so let's see now. Maybe we can talk this up there. Okay, because but it's a good point. It's something that actually you actually need to care about, because what the procedure we check to make this not NPR, there is playing again, as you said, with the precision here of the variable, you may find a worst case that is actually not computable, okay, but because of the precision. Okay, but yeah, so this is in an abstract way. Okay, so let's assume that somehow you want to reach the solution with some precision. Okay. But yeah, some point. Okay, so let's go back to this. So what we started with these multivariate polynomials, and so before we say, okay, I've settled the gap. So we have your experiment, you assume that you can, for each function for the experiment, you can understand if this polynomial is positive or negative. And in this case, are positive. And we say, okay, now we want to restrict the class of positive polynomials. The class we want to accept two things we can be sure that are positive. Okay, so we can compute easily, okay, if they're positive or negative. Okay, to do that, we did the following. So we changed the axiom of the tautologies. Okay, the game positive, we say, no, we don't accept all the positive polynomial gamble, we accept only the ones that we can certify in polynomial time, so with an easy procedure, if they're positive or negative. Okay? So we can take, for instance, an algorithm that can certify this in a polynomial time. Okay?
So you're changing the background.
I change the background. Okay, so I change the background, and we try to motivate this change of background from a computational point of view. Okay, so in the sense that since we are doing the experiment, we want to apply this theory. When we apply this theory of desirable gamble, we have to tell the things that they are not ideal. Okay, so we cannot accept a positive gamble for any gamble. We have to be able to check that this is positive, And so I change the background. Instead of accepting all the positive gamble, accept all the gamble that are assessed, whose positivity can be assessed in easy way. It's the only one that accept. Okay, so, and this is basically the only things that we change in the theory of desirable gambles. So before we had accept all non-negative gamble, now we accept all these, I call it the orange gambles. Okay, so the ones that are easy to assess. And this POSI, the conic closure is the same, we change it. And instead the sure loss or the accepting negative gamble, we change to accept a gamble that is negative, but we can easily assess that is negative. Okay, so I do all this change. Why? Because in practice, when I do an experiment, if I want to apply this theory, I need to verify this. If I cannot do it, I cannot apply the theory. Okay, so we change this to this, and then we can compute the dual. Okay, the dual, change the background. So it's what Gert said before. We are changing the background, and then we compute the dual. Okay, so we take the cone of desirable gambles that satisfy this property. We take this dual. Okay, the dual you can see is actually the same. Right, the same. The only difference here that instead of verifying this for all the positive gamble, I verify all the gambles that are easy to verify to be positive. This is not changed. Okay? I can do the extension of this to the charges, so this finite additive measure, and this maps to this. Before LG, I can write with this expectation, I expect this measure. But now, because of I changed this, okay, I don't have anymore the property that this measure is non-negative. Right? So what is this? This is a measure, a charge, we call it a charge mode, it's a finite t, that is just integrate to 1, but is not necessarily positive. It can be positive or negative. Okay? So it's a signed measure before. So in this case, the dual in the space of measure, or in the space of integrals, okay, with respect to these charges, I can only do basically allow this to be signed measure, right? By only changing the background. Okay? And that's it. Okay, so at the end we change this T. So we started with this problem. We want to do this theory of desirable gamble. We have a problem that we want to assess the positivity. These functions, okay, this is standard desirable gamble. Still too hard. We change this with something that is easier, and so we call this a sort of computational rationality. So we want it to be rational in the sense we don't want to accept a negative gamble. We cannot ensure that it's too hard computationally. We just accept this. Okay. And this verification now can be done in polynomial time. Okay, so I can do it easily. And so, and now things basically become strange because what happens here, that if this is rational, so if I accept a negative gamble that is orange negative, so it's negative, so if this is true, okay, then also this is true. But the other way around is not true. Okay, so here I can accept a gamble that is negative here, but not here. Okay, what does it mean? So this is at the end what we proved that because of this, we end up what we call the weirdness theorem. That is the following. Okay, so if we basically we take this subset of the positive gamble, the positive polynomial. Assuming that this set always includes the constant gambles. Why? Because the constant gambles are easy to us to evaluate. Okay, so these should always be there. And then we denote by this the negative gamble. So let C be a set of desirable gamble in my vector space that satisfy this B0 and B2. Okay, so with this definition of B negative and non-negative change, right? With this orange definition, easy to compute. Then these statements are equivalent. Okay, so if my call includes a negative gamble, so that is not in here, so a gamble that is negative but is NP hard to assess, okay, and this is valid, so this cone is still going to satisfy these two, right? But include a negative gamble. So a gamble that is blue, right? my cone includes a negative blue gamble, then we have this equivalence result. So if I do the positive gamble with the gamble that I set, this is incoherent. Okay, so it means that I cannot represent, okay, this cone here with basically a dual that has probability charge. So I have to move to signed measure. Okay? The dual of this cone this is where evaluation function comes from. So it's a closed convex set of mixture of things that are not classic evaluation function. Okay, so it means basically that if you change this background, you end up with evaluation function or extremes of the mixture space that are not classical extremes. Okay, so there's something there. It's what we have in quantum mechanics. Okay? If I extend this dual to the set of charges, okay, the charges are signed measure. So it means that I can reconcile my theory here, not with probabilities, but with something that is a negative probability. So negative and positive. Right? So these end up, okay, all together. And it's a property about restricting this property. Okay? So what we did is, and then let me stop with this, just to show you that quantum mechanics, what we did is actually an instance of this theory. So this is the last step. So we, as I said, what we need to do is to build our possibility space, build those polynomials, and then apply the theory. Okay? So we started with this possibility space that is complex number in a CN. So we consider, for instance, first a single particle and level system. So our X, that variable X, as you see, is an element of CN. It's norm 1. So we take this space. This is bounded. So my polynomial that I'm going to define on this omega is going to be bounded. And what are these? You can think this being the direction of the apparatus in the Stern-Gerlach experiment. And then, so this is for one particle. This is my possibility space. Then I can build the possibility space for any particle through the Cartesian product. And then what I have, I build my polynomials. Okay. So what do I take? So any basically complex polynomial, okay, of that from the complex variable to R, it can be written as a quadratic form. So if I take one particle, so m equal to 1, I can write any polynomial. This is a vector, Cn. I can write any polynomial that take from the complex number to R as the variable transpose the Hermitian matrix times the same variable. Okay. This can be done for any polynomial. So if I have m particles, I build my gambles, I multiply these polynomials and take in the span. Okay? Because I want a vector space. So remember, I want to have a space of gamble that is a vector space. So I multiply them, combine them, and what I get in this case, I get this. So I can write my multivariate polynomial for m particle as this quadratic form, where I have this tensor product, this vector, partial transpose, conjugate transpose, Hermitian matrix, and this. This is a quadratic form, it's scalar, so the value here is real number. Okay, so evaluating these polynomials, if I have m variable, is actually NP-hard. Okay, so if I do an experiment, I represent this direction, and I want to check if this is positive or negative, it's NP-hard. Okay? So I cannot do that. So what I'm going to do is to introduce a approximation. So instead of checking if this is blue negative, blue positive or blue negative, I'm going to check if it's orange non-negative or negative. So to do that, I need to define a new definition of non-negativity, and the definition is the following. So that gamble here is, I say, it's non-negative if this matrix is positive semi-definite. Okay, why? Because this is what happened in quantum mechanics. So I'm doing this, I'm observing this. So remember, I am in an experiment. I observe that when my experiment evaluated the functional, or this, if this is PSD, the result is non-negative. It comes from nature, the evaluation. Right? This is what I observed. And actually, And I think that to assess that is easy, okay? And computation. If I do that and apply my duality, I'll go back to these two. I first apply this. So I want to divide the linear functionals. The linear functional are this. So G is that matrix in the middle of the polynomial, rho, density matrix. Okay, so what I get before called the P, capital P, I call it the capital L, is this object. So you can prove that the object is this. The set of states is the set of density metrics that are positive semi-definite. Yeah. This is the equivalent of that operator L for this particular case. And so why is the case? Because the operator of the polynomial, okay, you can show that is equal to the trace of that matrix that is in the middle of the polynomial here times the density matrix. Okay. So what is this rho then? Is my operator L applied to this matrix. Okay, so it's the proof. So take an example where we have two particles with dimension 2, like a qubit, and then you have this polynomial. You take your L linear form. See, through the property of the trace, you can write this linear form as the trace of GL. So L and trace swap because they're both linear. And so you end up with this. Okay, so this is column vector times row vector. This is a matrix, and I apply my linear operator to this matrix. Okay? These are matrices of these monomials. I apply to it element-wise, and I define this as a row. And the row is the application of the operator to this matrix, to the variable of my polynomials. So, and then you can see that in this case, 4 by 4, you get this density matrix. So this one here is the L of this. So you can see, you can also check for the property of this monomial that this sum to 1. Okay, so it's done. And now what we can do, this is the nice thing about this, we can try to write this operator as the integral with respect to a measure. Now let's try. Can we write basically this as this being a probability measure? So the theory here, and I was thinking about this theory I have developed, tell me that if I have only one particle, so m is equal to 1, I can always write the density metric as an integral where this is a probability charge. Sorry, it's a standard probability. Okay, so why? Because for one particle, so for polynomial of one variable, okay, dimension n, but only one particle, okay, this definition of positive are the same. Okay, so for one particle quantum mechanics, these two are the same. So there is no, but one particle quantum mechanics is always compatible with probability. So you can always write this as this. This integral of this. So what is this? Is a moment matrix, a covariance matrix. Okay, so you can think about the rho being a covariance matrix. Okay? For two particles, the same. This is the result. In this case, since these two definitions of positivity are different, this and this is a charge, so it can have a negative bound. Okay? So you get again covariance matrix, but you are integrating something that can have negative bound. Okay, and so you go back, and then I stop to these two assets that we saw before. Okay, this classical probability, not theory we saw before, is the only theory in the framework with unique decomposition of all mixed states. Okay, so this statement in the framework we have seen is not true. Okay, why? Because in this framework, what we have derived that the rho is a covariance matrix. Okay, and for a covariance matrix, there may be two probability distribution, okay, that have the same covariance matrix. Okay, so if we see this quantum mechanics in this space now with polynomial and operator, is not through this. Okay, so already, no, so basically in classical probability theory, if I do the same for one particle, I can do the same. Okay, it's not true that exists only one single mixture. Okay, can have infinite mixture that have the same covariance matrix. Right, apart from the case where this is an extreme. Right? And again, so this other statement is not true as well. Okay, so because can have infinite, we call it Bayesian, so decomposition of this measure. Okay, so I will just stop here. So there's another result about how this is related to the witness theorem in quantum mechanics, but I will skip this and end up with this. Yeah, so some of the papers, if you're interested to know more. And I just want to mention this because something that Gabriele, also Gert mentioned before. So we applied this theory to indistinguishable particles, so like to bosons that are indistinguishable, and basically using this theory of polynomial. And to do that, what this allowed us basically to derive a theorem that allows us that you have a system that you basically couple with other bosons in the environment, and you increase the coupling by increase the number of bosons around, basically, and you look at your system, but this coupling is increasing. Basically, with this theory, what we saw that the orange definition of positivity converges to the blue. Right? That is what Gabriele said before. Was if we have basically we can explain it by how quantum mechanics converge classical physics. Okay, at basically when the number of the couple with the environment, particularly couple to increases. Right? So this is as a result about this. And yeah, this is my final slide. If you have any questions.
Well, the break would be scheduled now, but we can take some time to discuss. Yeah, go ahead.
One immediate question, perhaps very short.
Yeah.
So you change the background, right?
Yeah.
So typically for the background of the non-negative functions, the associated infimum operator is the infimum of the count. So what is the infimum operator that is associated with this background? Do you know? So the buying price functional associated with the sets of desirable gammas.
Yeah, I guess it's the cone. Okay, so if you see, it's the open cone of negative definitive. That's I think, but I'm not sure. Okay, so that I need to.
So that would be interesting to connect with my talk.
Yeah.
Questions right now? After the break, we'll have an open discussion to figure out what we want to discuss more in more depth during the different sessions tomorrow.
Sorry, you said when you change your background, as you say, and you weaken, like you throw away less gambles, right? You only throw those where you can decide in polynomial time that they're bad. Then somehow at that point, negative probabilities in some sense enter. Is it okay? Okay. I'm just trying to connect all of this to things I know. For example, like negative probabilities remind me of Wigner functions. Wigner functions are a way to represent wave functions on phase space. Then you have negative probability. And if I hear that, it sounds a bit like you can use these and they have negative probabilities, but you couldn't decide in polynomial time that you had a Wigner function with negative probabilities or something, that something was weird. Because it would take, I don't know, it would be too hard to experimentally find out that this is true or something like that. I don't know.
Yeah, you have to realize. So we were thinking about to extend this in the continuous, so in the infinite dimensional case, to basically try to match this with the Wigner functions. In at least maybe not directly because they are not exactly the same, but they are related. Okay, but you are right, and try to understand there how you can basically have this sort of computability axiom also there too. That is not clear to me. But yes, it's something we were thinking about to do.
And similarly, I'm wondering if this condition of like computability can be rephrased somehow in like a topological sense of like what we have verifiability. We also have like limits on like countable, sometimes what is it? If I already know for countably many sets,
So there is a lot of work done on topology and computability in computer science,
okay,
which I know nothing about. But one of the takeaway is that computable functions are continuous, but not all the continuous functions are computable.
okay,
And there is ways to do, essentially what you do is create these lattices of partial functions, right? That give you the partial computation, which means that you end, right? And then you study the properties as you know, the time goes forward, right? But it's always finite.
Okay.
And then you have maps that maps these lattices to other lattices. But there is a way to talk about, like a lot of stuff that people do in reverse mathematics also is about computability, about encoding structures in structure that then can be computed on and so on. But I don't know how they would connect to it.
yeah,
If you define an indifference as two gambles are indifferent, if you can't find out in polynomial time that they're different, you would probably go from the original theory through representation theorem via that indifference to your theory, I think.
Yeah, I think so, yeah, should be possible, yeah.
That's cool.
Yeah, so maybe just a little comment. So this is something stupid about, probably is easy to understand, but it's quite a key point between those symmetric cones. So so if you take the cone, the positively semi-definite matrix, so the cone of PSD real symmetric, right? And so take for instance the 2x2 matrices, kind of the equivalent of qubit, but with real, these are the real numbers, okay? And the cone is the cone of PSD real matrices. Take for instance this matrix, this we call it observable. This is X2. I didn't put the symmetric part. Put only X2 here. So if you do the tensor product of these two, okay. So since you have 3 degrees of freedom here and 3 here, because this is symmetric, okay, the dimension of the basis of this tensor product is 3 by 3, 9. Okay. If you take the 4 by 4 matrices, this is 4 by 4. Okay, so you find all the possible PSD 4 by 4 matrices. You can see that the number of the degree of freedom is 10. Okay, so this is basically so it means basically when you take the cone of or the sim cone of the real PSD matrices, then you build through this composition. You want to go in dimension 4, 2 by 2. Okay, you cannot do by taking, for instance, the span of this, right? Because there is some element missing, right? For Hermitian, okay, because you have this complex here, so this it's a Hermitian matrix. So this is going to be real. This is going to be in general complex. Okay, so if you do this then this, again, this is the complex conjugate. Yeah? So you have here 4 degrees of freedom and 4. So this is 16, but this is also 16. Okay, so this property of that cone of Hermitian is it's the only cone among those that satisfy this. Okay, so the tensor product basically it's in somehow if you take the span of these, okay, you can get the same dimension, same vector space. With the real matrix, you cannot do it. And now, what is important? So in the generalized probability theory, this mathematical property is usually used to explain why. Why, for instance, complex numbers, or why the cone of Hermitian matrices. Okay, because it satisfies this. So you have a composition that basically you can close and get the dimension that you have. So this doesn't work with real symmetry. So it's why you cannot do quantum mechanics with these matrices. It's the way it's often derived. And yeah, just a curiosity. This is what I mentioned. It's the tensor product that makes the difference with those codes.
I would propose we take a break
Yeah.
now. I think the Zoom at our originally scheduled time of 4:30. Okay.
Can we go on the video?
we start this, though at this point we might be. I do this, am I spreading things more around or might actually be?
In here, in case anybody.
Yeah, exactly, before people steal. Okay, so if I write. X. Does it go to the camera? No. Hello. Does not listen to me at all. Ah, there it is. There it is. And we can read the topics, so maybe I should just go closer. Yes, I should just go closer there, so. Right, I know, closer. Okay, and here we are, yeah. And probably Christine may want a computer. Which means. No. You can have your computer now. There was nobody right now. So. I definitely will want to talk, to have Marcel discuss sort of field theory, probability on field theory to understand what it does and how it does it. No. Alright, so we should take turns. Shouldn't be greedy.
We already have one topic, basically the integral, right? The non-additive
Yes.
integral. Where we first need to explain again, like what exactly we want.
Route for partial capacity, F cap, right? There we go.
As I said, I'd be interested in at least at some point trying to get some ideas about how to extend the things that I've been doing to infinite dimensions.
So
any help you could provide on that point?
dimension for symmetries on backgrounds? Or?
Yeah, for backgrounds. Yeah.
And related to that, I would also want to talk whether the Y permutations are not enough.
Yeah. Now, indeed, given what Alessio there wrote there on this, what was it? The Jordan thing? Yeah. There might be things there that could help find out where permutations could be enough.
What would be permutations in a quantum context, like reordering my basis or something like that?
In the quantum context, it's a unitary.
So how would you want to characterize this symmetry? Would be the continuous automorphisms, right? That would be the thing that we want.
Continuous automorphism.
Right, automorphisms, because if the space is discrete, then any permutation is continuous.
Yeah.
And so that's the permutation is the space of continuous automorphism for a discrete space.
Mm-hmm.
If we are in Hamiltonian mechanics, right, then what's going to happen is that the entropy will tell us which are the automorphisms, because you're mapping probability densities around in the same way, right? If you don't use the group transformation with Hamiltonian mechanics, you are going to have some probability that stretch and shrink, which is not what you want in the context to be able to define what are these symmetries.
But automorphism means whatever structure I already put on, this I'm preserving all of it, right? That means different things in different contexts, right?
Yes, but in the space of sets, the automorphisms are.
Yeah, exactly.
Yeah.
I just wanted to clarify.
So, okay, maybe I'm tautological, because if I'm saying that I have a continuous structure, then the automorphism is automatically continuous. But
No, I think
Yes.
the class of what you call automorphisms determine what the physics is, in a sense, right? Or the other way around.
Well, the
Like for
terminology
me, for
makes
a
sense.
classical experiment, only permutations make sense. From a classical
for
experiment.
discrete, because for me, classical is phase space.
Ah, well, yeah, okay.
a lot more,
Well, yeah. But
Yeah,
for me,
so-
classical experiment is just, yeah, but that is a classical physics. Yeah, I see what you mean. For me, this is just a classical statistics experiment where you have a set of outcomes and the functions on a set of outcomes are the random variables.
Right, so
No, you have the discrete outcomes is what you're thinking, really.
Yeah.
right?
we have classical discrete, classical mechanics continuum. And then you have quantum mechanics. So we distinguish these three cases. So this is a space, if you remember the first slide, one of the first slides that I had. This, the space X, is a countable collection of elements, right?
Yeah.
And the topology is the discrete topology.
Yeah, but for me, the second one, I also have the permutations there. But if
No,
you need more-
the second one is gonna be a symplectic manifold, well, X omega, and then typically this you can think it as R2N.
Okay.
But
That's
even
for-
as a step in between, like just a continuum, right? Doesn't matter if it comes from a
Yeah,
symplectic
that's
manifold.
what I meant.
Even
That's
on the
why-
continuum, it's like it's very different. Like then you can't just permute every single point on the real line.
Yeah.
You're gonna completely mess it up. There are well, you have to preserve the open sets in principle. For every open set, I could tell you whether you are inside in that open set in finite time. Because an open set is a small neighborhood and I have a finite measurement that I can make to tell
Oh,
whether it's or
okay.
not. If you map every point to every other point in some random way, you have no idea anymore.
You break the topology.
Okay, so
So
you
you really
need a
need
topology, you
continuity.
need or a metric, or is it?
So if you just have R, what's gonna happen is that you want to say the space of translations.
Hmm.
That it's like saying a measure on R.
Okay, so you need some way to say that distances are preserved as well. You know?
Like in your case, it's not the distance that you're worried about, it's the probability function. Because if you have, let's say in this region, a uniform distribution and you move it, you want it to remain a uniform distribution.
Why?
Because if you're allowed to move it however you want, you have the space of all possible changes in probability.
Yeah.
I think you're not gonna get what you want.
Yeah, I think so. I think that's why, yeah, I don't need probabilities, right? I need an infimum operator that has to be invariant. My probability measures don't have to be invariant. It's my infimum operator that has to be invariant.
Right, you're gonna be able to change the
Like-
infimum.
Yeah, yeah, you think
Yes.
so?
Yeah, of course. So think it like this. You have a Gaussian. Now Gaussian has no infimum, which is
Because the argument that I gave in my slides works for R. It works for R. Just with the permutations.
the permutation is going to destroy the topology.
Well,
The-
doesn't matter. It works.
The uniform distribution with compact support.
Okay, so you're gonna have the space of probability that are gonna be absolutely continuous with respect to the big measure, and you're gonna have the space of discrete measures. Right?
But I don't have any measurability or anything. I just have super additive operators and I have a background. And the only thing that I have to require is that my background is invariant under all these permutations.
Yeah, but the problem is this: if I just give you R, right, and you make a map from R to R,
Yeah.
your probability distributions are gonna change.
Yeah, but it doesn't matter. It's a background that has to be invariant, not the probability distributions.
But I'm not really sure because basically, if you think about it, it's like you have like a gamble that is a function of a real variable. No, I don't think that you can impose permutation there. I think it's not enough. You need something. I feel that the invariance that you need there is different. So you can think about the polynomial, for instance. As an example.
Okay.
I don't know. I'm not sure.
Okay, let me try this. Let's see if because maybe you're right, but I want to make sure.
Okay, it's an interesting point.
So let's just get an interval between 0 and 1.
Mhm.
Okay. And suppose that you're representing things a la what's it called, like a Bayesian type thing, right? And you say, oh, I have maximum certainty. You would say, oh, then I have a uniform distribution. Okay. And then you have a map that it's x that goes to x to the third.
Mhm.
Now, what you thought was your maximum uncertainty becomes this,
Yeah.
right? And so whether you're here or here, the function that you claim to be your maximum uncertainty changes.
Sure, but
You don't care.
maximum uncertainty is never precise distribution. That is the whole point, right? It's the background that has to be invariant, not the linear provisions. Yeah. So,
We want
I
to
think-
invariant to different. like,
Maybe it's because you are considering gambles, right, which are like some kind of other function, positive, negative. You just wanna make sure you exclude all of positive.
The thing that I'm suspicious is how you're gonna tell.
Be invariant in your thoughts, no?
so the idea
So
is
you can map an element to another element, but the more mixed space can be invariant.
take anything from R. Then take a gamble, F.
Yeah.
And the transform gamble is F after T.
Yeah.
Right. And the idea is, what I'm going to impose is that F is in my background set of acceptable gambles.
Yes.
Then TT of F should also be in my set of acceptable gambles for all T and all F. That's what and there is only one set that satisfies this, and that is the set. This one.
Where is it then?
This is a background set, so the set of all gambles that have that is, and I don't need to put any restrictions on these. There's only one set.
I mean, positivity obviously is
Sorry?
preserved by any arbitrary permutation.
Okay, so
Could you get away with less?
I-
Could you get away with just continuous maps?
Probably.
Or would you somehow?
The only
have-
thing, in fact, the only thing that I need is the maps that map all R to a single point. That's the only ones that I need.
Okay, so basically you cannot, like, if you include this, then you're gonna be able to map, and you really want all the T's, you're even going to be able to map distributions that are absolutely continuous to one that are singular, or that have pieces that are singular.
But
Yeah.
I'm very much interested in how restrictive I can make the T and still preserve that set. So that is,
Yeah.
right,
okay.
so, yeah,
Maybe you can get it, if you have arbitrary functions, arbitrary gambles, right? They're
Yeah.
already arbitrary functions, then you probably need all of this, right? Because for every single point, you need to preserve.
Yeah, but you, again, like, in our
So
case,
you
we
would-
want them to be continuous,
Yeah,
so.
but for him,
so
those are
those
two steps
T's
then, right? He would need to restrict his gambles to continuous functions.
Yeah.
And then the transformations, the symmetries, then you might be able to reduce them as well to continuous.
Oh, you have to, because otherwise you don't have the correct space, that's kind of what.
He could still,
But
okay,
here's
otherwise
the
you
point,
you
if
would
want
leave
to-
the space
If you
of
want to
gambles.
understand to the infinite dimensional space, then you have to be in a topological vector space, and you have only to consider your gambles and your functionals that are continuous, otherwise you. Otherwise, you're getting
Okay.
all the set of discontinuous functions, which is,
Okay,
you know.
well then,
more than
isn't it
uncountable.
as simple as like, if you just restrict your gambles to continuous functions?
Yeah.
Then,
Yeah.
of course, you will have to map a gamble to a gamble. It will have to be these automorphisms, so. Like,
But,
it
well-
could be the same.
I think that's a very important and interesting question, whether permutations could be enough or not be enough.
Yeah.
And so
So we
perhaps
should-
tomorrow we can
Yeah.
have a brief discussion on
We're
this.
discussing it right now, right?
Yeah.
Making a list of discussions. Anything else?
Yeah, I guess not to understand this step, I would be interested in if you can show us about the lumping. So the two properties that you need, about, because I think that is relevant to this. That's what I understand, you work in the discrete case, and then to understand that we can generalize the continuous case, because that is not.
What are we doing?
Because basically Gert said that it needs basically two properties, the permutation and the lumping.
Yeah, but in fact, using this argument, I only need very, very crude lump. I just lump everything into one,
Okay.
and that's enough, which is why I think, I hope that if I could restrict myself to permutations of some kind, that would also be
Yeah.
useful. Yeah, anyway.
So this is basically a professional.
That's it. Yeah.
The question still confuses me, why are there not enough? Like permutations,
There
are
could
they
be
like in a
enough.
sense too much?
So maybe put the not between parentheses. So it could be enough, right? We don't know yet.
Okay.
Okay, so,
Just a little bit.
are permutation enough to define
Background.
background? Are, what are they called? Is lumping.
Necessary.
There we go. That always goes back to your knowledge. I give some space, you do make noise.
I think so. I don't know why the camera keeps doing that.
So before, when people were speaking, I thought that maybe the bouncing of them talking would come from that direction.
Ah.
But now there is nobody in the speakers.
Okay, I don't know if it's a whole discussion topic, but I noticed that we usually talk about the functionals that take the state to give us the expectation value.
Yes.
He talks about it in the other way around. He talks about the functional that takes a measurement and gives the expectation value, right? Like he had on his slides, like you can put either one as a subscript of your functional. Do you know what I'm talking about?
So you can have f that takes a state and gives you a number,
Yes.
or you can take the state that given a functional gives you a number.
Yeah, or you could just consider one function that takes an f and an s and gives an r, whatever you want.
Okay, that never seen, but
No, like. Yeah, it's like I think on Alessius there was a p of the two. Or not?
The P or the G, you mean?
I think you called it p, and I got something measured, so like a measurement and a state.
You were asking about where the sort of where the state was, and it was embedded in.
Yeah, yeah.
It was embedded in.
He embedded the
density.
state into the function, we do the opposite. Either way, like we just like there are these two sides. Either you first define your states and then
right. So if you start with the gambles, you're basically defining the observable first.
Yeah.
And then you recover the state by saying, that's function of the gamble.
So I'm just wondering if this is like an issue. I mean, there is this duality in some sense. We
Yeah,
can,
there is the duality.
but
In fact, what we want to, like in our framework, what we want to make sure is that the dual of the dual is the same thing.
dual, which is not self-duality. Okay.
No, it's not self-duality.
It's-
It's called reflexivity in vector spaces.
But is this related to what I said in my conclusion, that you can have sets of desirable measurements on the one hand and sets of densities on the other hand, and they're equivalent? And that would give you a probability distribution over the states or the density matrix, and a set of them on the one hand, and then a set of measurements. And the one is the polar, or the what you call you didn't call it the polar,
No,
right?
I didn't call it.
You call it the what is it? The dual cone.
The dual cone, yeah.
The dual cone. So this relates here. So
Yes.
the set of densities is the dual cone for the set of for the cone.
Correct.
For the cone.
And in finite dimension, it's always true.
You can draw.
In infinite dimensions, that it's something that a
Excellent.
property might have or not.
Yeah.
And so I've been last week I was going through these properties called the reflexivity.
Yeah.
And what was it? There were two conditions that one I could get because I'm nuclear.
Yeah.
If we can prove that we're nuclear, and the other one, I don't remember where it came from. I would have to go and look my notes. But if you guys are interested, I can tell you what I've.
Yeah, I'm wondering because whatever we could learn from this, like it doesn't directly fit into our framework unless we already know that we have this duality, right?
Right, but it's also the problem for them as well. Because if they start from the set of Gumbel, then define states and define, and then they find that the Gumbels on the states they're defined is different than the Gumbels that they started from.
Yeah.
So in the metric space that I was working on in these cases, it works, right? Because and in the quantum cases, because it's actually a Banach space, and it works. So this reflexivity always works in Banach spaces.
Yeah.
In the finite dimensional context.
Or if it's finite dimension, everything works. It's
Yeah,
not a problem.
yeah, but
Infinite
that's-
dimension, I'm trying to remember if that's the case, but I don't think that Banach
Banach
space
is
are
enough.
all reflexivity.
It's enough to have reflexity. That's clear. Yeah.
Actually, what we is quite a little bit of charges.
You'll have to check it, but
Yeah.
anyway. I thought that I had found a counterexample for that, but it's not that hard.
Yeah, maybe on this, because it's related. Yeah, maybe we could also discuss a bit of the cancellation property of the mixed space, because I find it intriguing that you don't want to assume it, no?
Yeah, I want to assume because I don't know how to justify. So that's so I put it here, right? Like CVT of topological vector spaces, and then what would be called cancellation property.
I think the cancellation property is related to the mixing property also for horse lotteries, right?
Yeah.
So there's in economics, there's an equivalent condition that is sometimes justified. They have reasons for justifying it. So it might be helpful to see if that justification works in physics as well.
Okay. The problem is that so we don't have a weight-one mix in physics. We only know how to mix, and we don't have really a way to compare the pieces of mixtures. If I give you a mixed, if I give you two mixtures, even if I tell you, oh yes, half of the mixture comes from that other process, how can you it's like you would have in classical and quantum mechanics, that it works because then you can take pieces and learn the pieces and so on. But in a I want to be be able to be sure, oh, this is going to work for any physical theory. And if I don't know what the constituents of the ensembles are, I don't see a way to justify the cancellation property. And then the other thing is that it comes out from the entropy anyway, from the continuity of the entropy.
I find it interesting because it's something also that in economics they do it, so it would be interesting to see why you don't need it, how you can record from the entropy,
Yeah, we can go through. Yeah, it's very simple.
It may be very wild, and I don't know if it's relevant, but at some point I would like for you to comment on at some point, and how can this fit also in the context of this constructor theory that is being developed in Oxford? So constructor theory, so the idea is that this is like a machine that only does allowable things that are allowed by the laws of physics. And so you don't describe.
And how do you know what the laws of physics are?
Well, okay, given a number of things, you don't know what they are, but the idea is that you don't know what they are, but right. you will assume. For instance, let's say that something that makes entropy increase is something that so a constructor would make entropy would never allow entropy to do. It's just a simple example, right? So there's like an effort going on to reformulate physics, not in terms of differential equations that look at time evolution of things and somehow predict, but to formulate physics in terms of things that are allowed in some way. So, for instance, by the energy preservation or
right, but that means that you already know what the laws of physics are in some sense.
Yeah, perhaps. Yeah,
and that's exactly so. Even the whole so. When we started working on really the complete physical mathematical theory, starting getting the axiom, one of the problem is how do you break the loops that you have of self-referential meaning and all that, right? And one of the problem is we need to define experimental verifiability. And of course, there is a circular problem. It's like you can only verify things that there are processes that allow you to do it, right? And so the way that the framework works is that we have to be agnostic about that, because otherwise and so the way that you do it is just you say that there is some oracle that tells you which things are verifiable or not verifiable. Mm-hmm. And then you sort of go from there, you construct things from there. Now, there is a sense where at some point you might want to close the loop in the sense that you say, if I have a physical theory, and in, physical theory for a particular system, and I'm saying that there are these physical processes, then I should only be allowed to measure things that the physical processes allow. This might be one of the justification of why the topology would have to be generated by the generator of infinitesimal transformation. Because you say, oh, those are the physical processes, and if I have different generators, then I'm able to distinguish states, because if I put them in different physical processes, they are going to do different things, and therefore it makes sense so that the transformation generator of transformation are the ones that generate that topology. So in that way, you are kind of closing the loop, right? But it has to be done physical theory by physical theory. Because in classical mechanics, you're gonna suppose that there are different processes that they are in quantum mechanics. And so if you want, we can go and look, but I don't know.
No, I was just, I don't really insist. I was just wondering.
I never heard of it.
Yeah, but I only have a vague idea anyway, but
Yeah.
but I was intrigued by.
So let's put it like in our context, we have thought hard on how to break the loop to really avoid this circular reasoning.
Yeah.
And at the fundamental level, the sort of the ensemble space structure cannot tell you what the physical theories are. And it is another reason why we want to delay composition as much as possible. Because the more that I can prove just by the fact that, oh, I have ensembles and they have to be well-defined in a certain sense without talking about anything else. I don't even have time evolution right now. Like nothing that I said requires time evolution. One of the open question, for example, that we have is whether time has to be a real number. If there is, because we know that, so we have another work that basically tells us what are necessary sufficient condition for a quantity to be thought as a real number. And it really is a model of reference scales. So, I have a weight, and I reference weight, I can tell whether something is greater or smaller than the weight. And whether it's the same, it's kind of a little bit more difficult, because you can say that it's exactly the same. So you're going to have, so essentially you have these references where there's something is before, after, or on your reference. It's a set of three things. The before and after are verifiable, so they're going to be open set. And the on, maybe not, it's completely unknown. And then we sort of turn the crank and we say, okay, if I have a reference system, and I consider all the possible references, what are the set of minimal necessary and sufficient conditions such that the set of references can be understood as all living in real numbers. And it's a completely idealized set of conditions. And so we can't imagine that, time, wheels, or even space satisfy those conditions. So one of the open questions for us is, could we have a theory where I have an ensemble space that I will hold those nice properties that we have, and we have time evolution, but time is not necessarily a fully ordered quantity like R, but it's something else. And I don't know.
Yeah. I was thinking about this because I was trying to, work a bit on the Lorentz cone and try to work on the time. And I thought that, you may not need to define time as a real number, but I guess you still need to define a sort of, let me call it, I don't know, preceding relationship on events. So something that this comes before or after, and because it's a sort of like order, like we saw it in the economics, so the kind of order. And because basically, if you start with that, so you have some event and then you say, okay, this comes before for this observer, and then I think from there you'll be able, through representation theorem, to derive a real number representation of a time function. So something that tells you that the t of an event comes, I don't know, value 5, t of another event, value 1, so 5 comes after 1.
Right.
It's like that.
So the problem is that in a physical theory, when you write t, and you write X of T, right?
Mhm.
This X is all the collection of all the possible setups with the same, and also T is the average of your clock. Because even when we define time through, your verbal time,
Yeah.
it's you take a bunch of things, you do the average. So there is already a sense in which time is an average. So what would mean is that you might have a partial order, right? So you might say that this is before this, but if two events are too close, you can't say because your clock jiggle. And so you're not gonna be able to say that one is before the other because that before and after relationship is not. So there are two ways out of this. Either you have essentially an order structure that for points that are far apart, you can tell, and for points that are close by, you cannot. Or you basically say, oh yeah, but since this is an ensemble anyway, you're taking ensemble averages. And then that T is gonna be a real number, not because the order is defined, because you have averaged out all these things.
Mhm.
I don't know which.
Yeah, but because this one, when we talk about order, the indifference class, this is also related, to this idea of how you manage the border, things that are indifferent, And I think there again, is where imprecision can come from, the fact that you cannot say, for two events at the same time, who comes before or after, and then you can try to deal with this sort of, don't care about the border, maybe just care about, what is you're sure about comes before or after. So these things, I think they are all related to the discussion about indifference. You didn't find this indifferent class. And I guess by duality, maybe you can talk about average of time. I don't know what it means in that case. So yes, I was really wondered that because to me, as you mentioned, the two problems when we were discussing all day, and they seems to be very related.
Okay, so we have sort of the whole mathematical proof that tells you how do you get to real numbers. And the interesting part is that the hard part is not the real numbers,
Okay.
it's the ordering.
But because I was thinking that you should assume the order.
I don't assume the ordering. I give you necessary and sufficient condition of when you would have the ordering.
Okay, maybe, I think it would be interesting because I need to understand what you mean with.
I think that's an interesting.
Yeah.
Okay.
And if you have mathematical structures that you work with that are where you have an ordering for well-separated points or cases, or whatever, but are not well ordered for nearby points, that would be very interesting to have, because we need to figure out what kind of structures we want. Right now, we just say at some point you don't have the ordering, but we don't know how to sort of continuously go from.
Yeah, but we need to do it topologically again.
Yes. Yeah.
You basically there should be a topological space where the ordering is not defined at close scale, but it's defined at big scales. And then in some sense, you take the limit of that and you get the real, or you get a linear order.
Yeah, I was going the other way, and somehow try to find the background in this ordering, and then use that to define a metric through the basically the order topology. So I was thinking about it, but I don't know if it works. I never tried.
Yeah, we do the opposite. It's like we have all these open sets that come from this is before this reference, this is after this reference, and then we ask when do we get an order topology out of that?
Yeah.
It's exactly that. It's completed at a fundamental level.
Well, don't you always have the topology, even though the order is not like the linear order? Or not?
I have the topology.
It's always there, right?
Yes, topology is there, yes.
So, okay, is there some kind of, okay, so this order is not complete, right? It's like a partial order. I cannot tell for the element in the middle which one is before the other. Is there like some topological property that corresponds to that in some way?
You can create open sets or a sort of an order topology from a partial order.
Yeah.
You can probably do that.
And then you impose a condition for this to be the topology on the reals, is that? or?
No, at that point, it wouldn't be a topology on the real because you know that your set is not linearly ordered.
Yeah.
So you just have a partially ordered set.
No, I know, but so you will have an order topology, and then you can ask yourself, when is this order topology? Because you say you end up with the reals at some point.
Yeah.
So we end up with the real because we have enough assumptions
To make sure that this order
that this
topology
point
coincides
is
with the
You need exactly the linear order, right?
Yeah.
You need exactly the linear order to get such that the order topology is the real line, is the standard topology on the real line.
Yes.
That's a Cantor,
Euclidean topology. Or what?
oh yeah, standard topology on R, yeah.
Yeah, it's the topology around.
Yes.
So essentially what you have is that when you have open sets can be one inside the other. And that's it's sort of an implication order. And that's the stuff that you always have. And if you have an actual order set of points, that order on implication on open sets becomes isomorphic to the order of points. And so you have to figure out exactly how that works and what are the necessary and sufficient conditions. And then you realize, hey, you're thinking that you can do all these things.
Yeah, but even though you would usually define it in terms of like a Euclidean distance, we don't know what distance is on.
Correct.
We don't care yet.
We find the topology. We don't find the
Yeah, sure. Yeah.
There is no addition on these real numbers that
Right.
we understand. We don't
Yeah, but
know what.
once you have the isomorphism with the real line, you have addition, right?
No, just
No?
as a topological line.
Okay.
They are the same. They are not.
Because again, you can make a
fields.
linear transformation and the linear structure is broken.
Yeah, okay. We already have quite a lot of stuff tomorrow, or do you?
Yeah, I was thinking that, we kind of make a list and then we pick the ones that are more interesting or we send them to them. And then, we always pick the one that we're most interested in discussing at that moment.
Yeah. I was just wondering if this might be interesting. So there's some work that you can do on defining symmetry in a probabilistic context using the notion of indifference. Yeah, and that could be. I'm not sure if this could be interesting for the project, but if anyone is interested, I could briefly discuss that as well.
Yeah, symmetry from indifference.
Or the other way around, indifference from symmetries. There's a yeah.
Let's leave that for the day after.
Sorry, are you saying you can go backwards? Usually you define what you are indifferent about based on symmetries?
Yeah.
But, okay, right.
Yeah.
Very nice. Okay.
Because so a gauge theory should be something like that in physics. Because you are indifferent on the representation, and so it's a symmetry of the theory, but it's not a symmetry of things that we care about. Those are actually things that are still not completely clear to me. Because, for example, as we said before, momentum, equilibrium conjugate momentum in physics is defined up to a gauge, but we still put a topology. Which meaning, we can experimentally measure momentum. Well, you measure kinetic momentum, the conjugate momentum. It's only when you fix the vector potential that you can go and do these relationships. So it's yeah.
Yeah, bizarre, what a big deal. Gauge symmetry is made of gauge symmetry in physics because it's, symmetry with respect to the unphysical piece I stuck in my mathematics. It's like, well, that's not really a symmetry of nature. That's a symmetry of your artifact, right? So, but people kind of act like it's a symmetry of nature.
Yeah.
It's funny because like in gauge theory, you talk all the time about what doesn't matter, but this is the most important thing. Like the gauge doesn't matter, but some of this is like, maybe it's like you just constrain it enough such that you know then what matters.
Yeah.
But anyway.
Well, I think it's going to make a fascinating video discussions.
You have something that you think that man might be interested in, or what we?
So that I'm
So
interested.
that they could be
They
interested
could-
in.
Well, we already talked a lot about topology, and I don't know, like, for us it's very important, and I've seen like different ideas that are like related, but we phrase them specifically in terms of topology. So if we can bridge the gap and like translate between these ideas, I think that would be very useful, because for us, like, topology is like the most natural way to say yes.
And there is a lot of work that you can.
Yes, but I think it's like already hidden in like many
In
of these topics.
this.
But if we get it like once, right, so that we are on the same page, I think that will.
Topological convex.
Yeah.
Those are open questions. I mean, I can go through a list of open questions on these things. I don't know if, how much do you guys know about convex space in general? Do you convex optimization, stuff like that?
But yeah.
Oh, okay, then we should definitely talk about that. That's
Yeah, but I never realized that there was such a thing as topological convex spaces as opposed to topological linear spaces. So
I made them up because I
you
knew
made them up. Okay,
Yeah, the
cool.
point is that you're not, it's not a thing.
It's not a thing. Well, it's a
We-
thing.
would be a
It's a
thing.
thing.
Somebody else contacted him and then it's like.
eye contact. So there are some people that worked, so I don't know if you heard John Byers, one of the mathematicians, and then there is this Fritz guy who also wrote like this very nice thing about convex spaces a long time ago before he actually changed stuff. So I wrote to both saying, you know, I'm trying to write, you know, to understand like how this topology works and so on. And they weren't so receptive, and at some point, John Byers says, well, you know, you should do it yourself. In fact, if you Google around, you see that topological complex spaces are mentioned or stack overchanged by you. Because like an idiot, you know, you try to ask everybody that doesn't, but
That's cool.
yeah, so the main thing for me is when do these things embed continuously in a topological vector space. So I can put it on the list. So TCS in TBS. And the other interesting thing is that when I start talking about topological convex spaces with ChatGPT, it understands immediately what I'm talking about.
Because it's you. He knows it's you. I have similar things in imprecise probability.
Oh, there you go.
Yeah, he told me somebody before he knew me said somebody wrote a book on that. So I know.
So 2 years ago, like, well, maybe 1 year ago, when ChatGPT was still crap, I was asking, and he said, "Oh yeah, topological convex cities, just started," and he would get this list of fictional books.
Cool.
They're discussed in this chapter of this book. I says,
No. Yeah. But it's related to the cancellation property, right? So in that sense.
Yeah, so the cancellation process,
Is
at
enough.
the end of the day, it's very simple. And
Is
as you
enough.
said, it's mainly.
To reduce the second to the
physical
first.
justification than anything. This is really a mathematical thing that we need to understand how it works.
Well, but you won't need it if you have the cancellation property, because then you can embed it. That's.
Now, if I don't have the cancellation property, I can't embed it,
Yeah.
and then definitely I don't. The two things are different.
Are different, yeah. But so the point is, since you can prove the cancellation property, you don't actually need this, or what?
No, I can prove CS in VS.
Ah.
I can't prove. I need to prove TCS in TVS.
Okay.
Like the embedded has to be continuous.
Okay. Yeah.
Like it has to be a topological embedding, not just an algebraic embedding.
Oh, okay.
So,
I didn't
for
realize.
example, you need to show that, let's say, PA plus, okay, so you have BI that does not converge to anything,
Mhm.
okay? but then PA, P bar B converges to some. Right, so you have something that does not converge, then you make a convex combination, now suddenly converges. That would be something that it's a CCS that does not embed in a TVS. Because if it embedded in the TVS, if this doesn't converge, this cannot converge here.
You had counterexamples? No.
Supposedly, ChatGPT gave me something, and I'm still trying to understand whether it mathematically works, and then I have to understand whether if it's physically meaningful or it's just gibberish.
Wait, which topologies do you use to decide this? If you, at the top, you use the topology on the convex space,
You are in the convex space in both cases.
and the convex combination is continuous by different.
Correct, it continues, meaning that if it converges, then this converges.
Yeah, but if you have now another topology in the embedding space, and they don't disagree,
You can, if you can do this in the convex space, then there is no topology on a TVS that will give you this. Because in a TVS, a topological vector space, this is gonna converge if and only if the BI converge.
Because of the cancellation.
Because the negative is continuous. Right?
Okay, yeah.
So all affine combinations are continuous. Like we don't know that affine combinations are continuous. We know that convex combinations are continuous. If all affine combinations are continuous, then it's like a topological vector space.
so the other thing is guaranteed. If BI converges to B, then this definitely converges, but
Because it's
you're saying the
continuous.
other case can never happen.
The never case cannot happen in a TVS,
Yes,
but it could happen in a TCS if you find something that does not embed.
yes,
And so the
okay.
claim from ChatGPT is that it found a topology in which this happens. And it has to be in the infinite dimensional case, because in the finite dimensional case, it cannot happen. And it's interesting because it's a topology that makes the entropy continuous, so that I satisfy the axiom, and makes it continuous in a way that it depends on how the tail works. And so when you do this, you kind of make the tail converge in a different way. And so this now converges and this doesn't. Anyway, I can go through the details of what and these are the problem of the embedding is understanding these issues.
This is
Similar,
really cool.
it's similar to saying that B is like the coarsest topology that makes convex combinations continuous. Is that related to saying that the topology is the coarsest one, the smallest one that makes the convex combinations converge? Maybe.
Right, and while you can make the convex combination converge, it's not necessarily true that you make the affine combination converge. And so those two things are different. And
If your counterexample works.
if your counterexample works, but then I still have the problem that it might be completely physical anyway.
Yeah.
And so it's like I do have counterexamples that are more mathematical and counterexamples that are physical. And the counterexamples that are physical, I used to say, this is not going to happen. So for example, I have a counterexample for which the ensemble space is not bounded in an infinite dimensional space, just in the space of discrete probability distribution. So I know that since that's a physical example, we want to have that, then we don't always have bounded subset. Which also means, when we're doing Choquet theory, we have a subset that are unbounded, that definitely not going to be compact. So clearly, you're not going to be able to do Choquet theory on those things, right? So, and then we need the different ways to sort of handle these. But and then I do have counterexamples. So, for example, I have a cute counterexample of a space that does not admit the cancellation process. And it's still a topologically convex space. So I can put a topology on that without the cancellation properties. So it satisfies the axiom of ensemble and axiom of mixture, but you can't put an entropy, and so it's not an ensemble space. So a lot of it is trying to find all these like little examples that sort of guide me. And it's only since this January that I finally figure out, have some intuition on the infinite dimensional spaces, because before I really didn't understand anything. And now I'm starting to finally get some sense yeah.
So since you're talking about entropy, is it completely clear to you how your entropies relate to the entropies that you were discussing?
No, I think that would be something that would be interesting to me also to check, because I'm curious how you can basically define the entropy in a sort of full generic mixture spaces, it's somehow in
Yeah.
This to me is something that yeah, it's
Oh, you sent me the note. Should we also add that to the list of things? to
yeah,
discuss?
the note was about the fraction capacity, try to understand how this relates to something that we know in the just for probability spaces.
Right. But it's not about the integral, it's just on the fraction.
No, it's about the fraction capacity, because I was trying to, because to me, as I mentioned before, I found, okay, this is something that we should have in probability, because it's related, for instance, at epsilon contamination. It's very similar, but although there is no the definition, because in the epsilon contamination, we keep the epsilon fixed if we move one of the other. Instead, you keep basically all the rest fixed, you move the p, and then I just tried to do the discrete case to see if there is something analogous, and there is that basically you can prove the fraction capacity is equal to what's the name? Basically a divergence measure that will come to me. Sorry, it's the jet lag.
It was the Renyi and
The Renyi divergence, yeah, the infinite one. So you can prove that the same in the discrete case.
in that case.
Yeah.
Okay, so let's put this because that's we should discuss. How do you spell Renyi?
Or even why.
Y
E.
I.
Then G, yeah. And the E.
Without
not
the
E,
E, without
the E, yes.
Yeah.
It's the Italian, the American.
Because if there is a relation between your two types of entropies, then I think we can use that argument also related to what I was doing.
Yeah, I think this for us is a question we never look at entropy, but maybe is a piece that we need, to be able to do some generalization, because somehow you need to fix something, and I think it's when you want to generalize, maybe looking at entropies.
So I told you the entropy. I realized that it's fundamental because I can't do classical mechanics without it, because it's the entropy that tells me the volumes in phase space. If you just have the probability structure on R2, you don't know which size the volumes are, because you change the volume, you still have the same space. It doesn't change anything, and so.
So does your entropy define a norm or a distance or
It defines this pseudo distance, but
Pseudo-distance.
it's not enough to do much with it. You can do some things, but so ideally, that pseudo distance, at least in quantum mechanics, for the pure state, it's equivalent to the inner product. Because this pseudo distance is basically 0 if you have the same state, and 1 if they're orthogonal to each other.
Okay.
So
1 minus that?
yeah, but then it's non-linear, so you need a function in between, but it's
Or the
basically
exponential of it?
no, it's the inverse of this horrible thing.
Yeah.
Yeah, no, it's not nice. And then -1.
Okay.
It's this thing. And so this thing here is actually is the square root, right? This is like it's this.
Is it 1 plus in the second one or also 1 minus?
That's minus.
Yeah.
It's this. This square root of p is just the norm of the inner product. Right, so and this is an invertible function. It's basically something like this. And this goes from 0 to 1, and this also goes from 0 to 1.
No, I was thinking about the result. I was thinking about also your work with lattice, no?
Yeah.
And I wonder if that defining an entropy allows you to define what's the name, the lower valuation. Oh, it's not called the lower valuation. Even in the lattice, now you have you can measure. What's the name? Oh, sorry,
Yeah.
start with some tired now.
In any lattice,
Yeah,
and it's precise in a Boolean one.
exactly,
Yeah,
exactly. What's the name?
okay.
That
Yeah.
one, yeah.
Okay.
If you're interested in lattices, so I had a couple of slides on the lattices themselves that I skipped around, but that could also be a topic. The difference between the separate lattice and the orthogonal lattice, right? The orthogonal lattice is the one that effectively becomes the one from quantum logic, the lattice of the closed subspaces. And so that again tells you that it's the entropy that is defining that. Because again, you can define things like this. So let's say that this is my block ball, right? Well, this now is orthogonal to this. Very cool, very interesting. Now suppose that I take a smaller block ball inside, because I say, oh, these states, I can never prepare them anyway, so they don't exist. And now this is not orthogonal to this. You do not have the lattice of orthogonal subspaces. And again, you don't have a probability between these two things because you can't decompose into things that are mutually exclusive, right? And so if you were trying to reconstruct the lattice of the subspaces from the non-entropic structure, from just the convex structure, you're not going to get the right lattice. Because there's nothing, there are not going to be any probability, classical probability outcomes of this. Because whenever you're going to try to measure this, right, you're still going to measure two probability distribution. One of the things, I don't know if you guys know what weak measurements are.
Yeah.
I have a hunch that maybe we can show that this is kind of what you're doing with weak measurement. Because now what happens is that, suppose that you still call this 1 and call this 0. The range of what you're going to measure is bigger, right? It's going to be, I don't know, 1.5 and minus 0.5. So these are the things that you're measuring. Then you're creating statistics of that such that the expectation are going to be 1 and 0. So you're measuring, you're trying to measure these two things, which are now expectation values. And you measure it on a spectrum that has nothing to do with the spectrum or the quantity that you would have.
Well, sorry, I don't know what we measure. Are these related to POVMs?
No.
No.
It's probably knee, but no. Yeah, so basically, no. It's a weak measure. It's something that when it doesn't block the state, when you do a measure like a projecting measure. Okay, so they are related to POVM. Yes,
Okay.
in the discrete case.
In the POVM, you're basically doing a projective measurement on the compass.
Yeah.
Here, you're doing something very, very sneaky. You have a system. You couple it with a probe, but very weakly.
Yeah.
So that they're in a very small superposition, right?
Yeah.
And then you project you do a measurement on the ancilla system.
Yeah.
And this, since it moved very little, you can reproject it on the original direction. And you with very high chance, you're just going to go back in the previous state. You can do it again. You recouple a little bit. So you take like 6, 7, 8 measurements of this. And the end is that you measure the initial state of this thing coming in with a very high chance. I mean, there's still the chance that you completely destroy it. But I saw experiments done in Italy in Turin. There is a group that does it.
So this is an idea to prepare your state in a certain sense, right?
It's like how you're conducting. So that you basically have to think of, and that's how they think it, as a strong measurement, a projective measurement, and a strong measurement that interferes with the system a lot, and therefore can get a lot of information out of it.
Yeah.
And with a weak measurement, you just you do it a little bit.
Well, a few times.
Right, a few times. Yeah, you can repeat it. What happens is that the spectrum of the measurement on the ancilla, it's different than the spectrum of the eigenvalues of the things that you're measuring. And so, and you have much bigger spread. right? So in, if in a projective measurement, the spin, goes from 0 to 1 or from 1/2 to 1/2, maybe the weak measurement can go hundreds out, right? So you could have a spin measurement that it's like 95, which makes absolutely no sense because it's very noisy, right? But then if you can repeat the measurements, then
You
you
get less noisy.
get less noisy, and then you can get, yeah.
And sorry, but so make it less noisy, does it mean that the variance goes as 1 over square root of n or 1 over n?
I don't know.
That is.
Then you have to ask the people that do these things. I have no idea.
Okay, yes, it's like. I think it's 1 divided by divided.
Yeah, it's strong convergence. Yeah, that's really cool.
So step 31,
Yeah.
I would suggest we have a dinner reservation in an hour, 20-minute leisurely walk away.
Did you type in the list?
I did, but maybe we should think about the order that we would initially, at least not the full order, but like what do we think we should prioritize for the morning?
I think we
Suzanne
can
and
also
myself.
decide it on the fly, depending on, like, we send them, everybody makes their own, and this would be my first thing, because Marcella is in
Yeah,
there in the
Marcella's
morning.
not as
And
personal.
other things about the integral might be better to discuss when Susanna is there as well.
Yeah.
Right.
Okay,
Okay.
right.
Would it make sense when we talk about field theories?
Yeah.
To talk, like give a crash course on topologies and sigma algebras, because for field theories, it will be, well, like, that's the hard part somewhat, right? Defining what
I
is
think
still.
everybody here knows what a topology and sigma algebra is.
Maybe, okay,
You
like
you
in,
mean-
in
you mean-
the- our
but-
interpretation.
Sigma algebra
mean from our-
From our
Assumptions of physics,
perspective.
you mean,
Yeah.
Okay.
You mean the Borel algebra?
Yeah. No,
Yeah.
He means how we generate them from
Yeah,
physics.
yeah.
From very.
I'm not sure if this is like valuable to do before we talk about field theories.
So I do not know, so I do not know what are the statements that we could have in C theory. So for me, that's a completely separate thing.
Okay,
Because what Marcel is gonna have, he's gonna have some recipes that you can have some things that look like differentiation, and they work to do some calculation, right? What is the mathematical underpinning of that? I mean, he already said it, like it's shaky, right? You just do it because it works and so on, right? And part of understanding how to do it properly would be to understand what are the verifiable set that we have in
Yeah.
field theory. And I have no idea how to approach that.
maybe this is then too far, like.
Yeah.
Then we can do it later. Okay.
You didn't have anything.
No, I removed it because for the field theory, I think we're gonna have enough problems understanding what those things are.
And the entropy and the relationship between fraction capacity and the Renier entropy are two.
Yeah, these are two different things.
What's entropy including here?
Whatever else you want me.
Oh, yeah, I was curious, in the way you use entropy, to prove things,
Yeah.
because I think that's.
And whether it's related to the notion of entropy that he associates with.
The Jordan algebra and symmetrical, that would be curious about, yeah.
Yeah, for that I can basically show you how we go from the axiom to getting the what's it called? The Shannon formula.
Mhm.
And then it's not in the book yet, but the point is that if you have a space that it's we say orthogonally decomposable. So if you have an ensemble that can be decomposed as the sum as the mixture of two ensembles, then you can do it with orthogonal mutually exclusive thing. Then what happened is that since you know how things like you have the formula for that, once you can go to a set of things that are all mutually exclusive, then you have the entropy formula. And since you can always do it for a density matrix, you know that the von Neumann entropy is the one. The only thing that you don't know is that all pure state have zero entropy. But that kind of, it's an assumption when you say that you have unitary evolution, because a unitary evolution is going to be deterministic and reversible evolution that has to connect things that have the same entropy.
Mhm.
And so all pure states have to have the same entropy, and then you call that zero. And
Okay, so you also exploit the unitary evolution.
like we don't have yet the argument for that, but it's it's the same thing that you do in classical spaces, right? In discrete spaces, you use the Shannon entropy, just that. You're assuming that the entropy of the points is zero, because you put one, the entropy is zero, so it's already embedded there. Okay, so I don't know if anybody is watching us anymore, but we can stop. And thank everybody for following, and we're gonna reconvene tomorrow. No, there is currently concurrent zero. There's zero right now. There's no.
In Europe, I think everybody's gone to bed. I think my students have gone to bed.